Everyone doing? Excited for Turkey Day? Silver Turkey Day? Well, pushing through the indigenous communities then. The what?
Like people already like, not people, but like, already like celebrated.
Yeah. Turn it into just like hands. Okay. Just to clarify, so as a really good professor, one of the things I like to do is to make sure you're engaged in the material. Don't put something wrong up on purpose. I'm just kidding. So my notes were totally wrong. And the first part of it, well, not totally. We got to the derivation of skin depth, right? And then we looked at these simplifications. And there's two important things I want to point out. In your notes, you might have this as mu over epsilon. It should be epsilon over mu, because that's going to give you the complete wrong units. This thing right here, epsilon over mu, has units of 1 over ohms. Okay. And
Sorry,
go ahead.
for a skin depth.
Yeah, this is for skin depth. And if you're looking at your units and you're like, oh, this is all fucked up all the time and I didn't know what was going on. Another way of thinking about it is in the context. So we have the conductivity, which is sigma, right? So sigma is defined as the conductivity. And the units are, I don't know, something. 1 over ohm meters. And the resistivity is related to the conductivity. Do you remember this one? I know that it looks like density. It's 1 over the conductivity. Okay, so that's why you see it twice here, right? So depending on what your reference might be, if you open up your book and it gives you the conductivity for water or the resistivity for water, now you can just grab the other one. And so the units for the resistivity very reasonably are ohms times meters. So now you should get very reasonable units when you put it in. And that first explanation of what's the skin depth for air. Anyone go home and do it? Okay, good, because I did. So the skin depth for air, can you take a little guess? My original estimate was e to the minus or 10 to the minus 5 meters. This is inaccurate. It's bigger, very good. Is it larger than a meter? Yes, how much bigger than a meter? 1,000. 1,000? Okay, would you be surprised if this number? Okay, so a little bit bigger than a meter. So air is a very good insulator. Right, so we knew that already. And what this means is, excuse me, what this means is that light at visible wavelengths can travel through air quite easily. Now, there is a wavelength dependence here, and that's really important. So that's the same reason why you get sunsets that have a red color, because there is more scattering at blue wavelengths than at red wavelengths. But we're looking at a monochromatic plane wave when we did this, but as you go into this, let's say you do graduate studies and you do radiative transfer, that'll come out automatically. Okay, is that okay for folks? Okay, you may or may not see this again. You take the exam on Tuesday. No, I'm not gonna do it on Thursday. It doesn't make sense to do it on Thursday.
Oh, that's what we have.
Yeah. So if I think about it, right, like what I'm doing right now is I'm kind of going off script, which is why it's all fucked up. And that has everything to do with the fact that I think radiation is so interesting because it allows us to connect moving charges and how they actually work in matter to our ability to probe them, to understand what they are. So we're gonna be, we're gonna look back at some Lorentz gauge stuff. We're gonna have to talk about that weird square symbol. Remember what that was? The French name? There you go, Allenbertian. So we're gonna talk about that today. And then we're going to derive the potentials from moving objects. Okay, the moving object potentials will give us our fields, they'll give us everything we want to know about it and let us know whether or not we can get waves, right? Okay. So this next couple weeks, whether that's Thursday and then the week following Turkey Week, we'll probably finish up radiation. And if we have time, we'll do special relativity. Because I think one of the most interesting parts of electromagnetism is suddenly it tells you about black holes, just out of nowhere. Yeah.
So next Tuesday, the exam, and somebody else will.
Yeah. So I'll just have however many people want the exam, I'll just have them be here and we'll just sit here and do it.
Who's gonna watch this?
Yeah. Someone else.
I don't know what that was. Okay. Other questions? Okay. Okay, so we were talking about radiation, right? What is radiation? Right. So the very last part is the part that I care the most about. Goes to infinity. So it has to show up at infinity. Right? That was our special definition. Okay. Do we need this still? You still need it?
I got it.
So let's work out some of those requirements that we had. So if it goes to infinity, then then what does this tell us about the particular E's and B's?
How many R's can be on the line?
Right. So we had this requirement that if I have power in my pointing vectoring, right? And this is going to be the integral of S dot dA. And the dA has units of, well, not units of, but is 4 pi r squared at some arbitrary distance. And so this thing here, if I need it to show up at infinity, then this has to have 1 over r squared at the least, right? 1 over r cubed, then S, or S times dA goes as 1 over r, and that disappears at infinity. But I want it at most a constant. Or at least constant. Okay. So P as r goes to infinity is going to be our definition of radiation. Okay. And the wonderful analogy in the book is that okay, you can have some charges and they can be doing stuff, right? And there might be like short stuff that's coming off of it. So there might be power emanating from those charges moving. What we care about is the stuff that moves really far away. And so the way to think about this, or at least the way the book talks about it, is that there's a garbage truck. On the garbage truck are a bunch of flies. And the flies are like, falling off maybe. And then some of the flies are being left very far away as the charge leaves. Right? That's very scientific. That helps you think about it, right? Okay. Okay. So our requirement for this one was that S needs to be 1 over R squared, right? So that puts what requirements on E and B?
So now it can be 0.
True. But not what I'm asking. They're both 1 over R. I want solutions of the form 1 over R. That when I cross them, R, 1 over R times 1 over R is 1 over R squared. Right, that was my response. Okay. Okay, so this is what we're looking for. And in fact, if you look back in your notes, you haven't seen a lot of this. We haven't really touched on the solutions that go as 1 over R. Most of our solutions go as 1 over R squared. Think about a point charge. E goes as 1 over R squared. Right? We started talking about electromagnetic waves traveling at the speed of light. And suddenly, if you start thinking about a moving object, now you have to consider that if it's moving, the field cannot instantly give you this information. Okay? So this makes us use something called retarded time. Okay? So T minus R over C. Okay, so this is the current time. This is the time for the observer. Okay, and this is the time at the point R. And this is R. Okay, that's some distance. Okay. So in practice, what does that look like? Here's a charge. Here's you. It's your eyeball. So you may be thinking to yourself, okay, some charge is moving in this direction. It has some velocity v, some q, whatever, right? The waves that are traveling to you, they're traveling from here to whatever your measurement thing is, whether that's your eyeball, if it's light, or some electromagnetic receptor, right? You have to consider the place where the fields were created is back in time, and the object has since moved, right? So if you're going to find out the total field, you have to sum the contributions from all of them. Okay, so you have to think about the particle going along the entire path, not simply where it is at a fixed point. Does that make sense? Okay, and I'm going to use this here because we know that it works. This is a form of a Galilean transformation, which you may remember from 2500. Okay. Yes or no? No. Okay, let's write this. Galilean transformation. X equals X naught plus what? V O times T? V naught times T. Yeah. Why is that right?
Because we not going to do just this.
Yeah. So this is some little distance. This is the original. This is the final. Okay. The reason we call this a Galilean transformation is not because this is talking about the moons of Jupiter and anything like this, but because this is the first time that we really wrote down in this sort of a format how equations of motion work. And that's some location now. If I just wait a little while at some speed, I'll be at a different location. But the realization here is that while that's descriptive of, say, an observer watching a cup move, it also turns out that if I am on the cup, it looks like I will go in the opposite direction, right? So this is a type of variation where depending on the reference frame, it can go the opposite direction. You see? So that's why we call it a transformation. Because what we're doing is we're transforming the coordinate system. We can move the entire coordinate system to the right, and that will act the same way as the object moving in the opposite direction, right? Okay. You may recall that we went over this a little bit when we talked about these things called gauges. Or gauges. Raise your hand if you remember what a gauge is.
Pressure gauge?
No, not like gauges, right? Okay. Let's just do a really quick recap. We're gonna go off script here. Hopefully this won't suck. All right, you may know this. This one?
Oh, zero.
Zero. What's that? Yeah.
That's the be not get some of the last thing.
All right. So that's kind of where we started in order to begin thinking about like waves. We said, well, if we take a second cross, we can get rid of some of this stuff. And we talked about with Ohm's law, we said, well, J is really proportional to E. And so that gave us these decaying waves into material, right? And I guess it was like 5 weeks ago. We were talking about, well, the fact is that mostly in the front of our book here, there is no E's and B's, right? Instead, there's these weird things. What's this one?
Potential.
What potential? Electric potential? Yeah, specifically the, there's a name, different name. Scalar potential?
Okay.
And this one is the? Okay, good. Okay. All right. So in practice, we can say something like this. B is related to the vector potential how? Yeah, that's it. Correct. All right. So we said that, and then we also said that E can be gotten from the potentials.
Negative gradient.
Right? And? Yep, it has to be. All right, let's think about this for a second. This is B, right? So this is our magnetic field. It's coming from our vector potential, specifically the curl of the vector potential. This one here, that's what we had in 2510, right? So you would just find the potential and then you take the derivative and everything would be great. But then we got all spooky with everything moving and blah, blah, blah. This is not just, 2510 anymore. This is electrodynamics. So we probably need one more thing here. So I see some spatial derivatives. So I want some time derivatives, right? So I can generate E by time changing A. That make sense? Okay, so when you're thinking in the back of your head, you're saying this is mostly represented by B. E has some time change of B. E has some time change. See?
Is the gauge what scares me with derivative?
Right, so what we did with finding gauge transformations is the realization that because I take a curl of this, because I take a derivative of this, derivatives of constants are 0. So I can arbitrarily like add whatever I want onto A and V, because those are never measured. The only things you ever measure in a lab are E and B. So the absolute value of A and the absolute value of V, they don't exist to us, they're theoretical. So that means we can have fun with them. Fun. Okay, single quotes.
So what are the gauges here? For all this?
So hold on. We can look back in the notes here, but you can do anything like this. A prime is equal to A plus delta of lambda, and V prime is equal to V minus the time derivative. Right? And this was a way of setting something that we called, which one did I create there? That's gauge freedom. You can create different choices for lambda. And the one that we talked about in particular was the Lorentz gauge. Okay. Spelled like this, Lorentz. Okay. Lorentz gauge is it's an arbitrary choice. Lorentz was like, I don't know how he did it, but probably just like a spit of genius one day. He was like, all right, I'm gonna use this. I'm gonna use del dot A is gonna be equal to minus not epsilon naught beta t. What was that down? That's too bad. Doesn't do anything. Okay. So in fact, what that does for us is that when we can put these together to solve for A's and B's in terms of our original equations here. And we can write A's and B's in terms of J.
So is a gauge kind of like a transformation, where it's just like an equation that you kind of use a lot, kind of the equation style?
Yeah, it's a way of framing the potentials. And what I mean by that is you set a requirement about V and A, right? Things that you don't measure. And you say, I'm only going to choose solutions of this type. Now recall that when we do physics, counterintuitively to every way that you've done physics in the past, you don't know the answer to start with. Okay, so you're in the lab and you're measuring something and the charges are moving around, right? You're like, oh, I have this like complex potential of V that's sitting underneath my measurement, which is I measured D and E, right, at all these different points. What you want to do is you want to work out what those potentials are. You don't know what they are ahead of time. So you can choose solutions that will better help you solve the differential equations. Because you're taking advantage of the fact that these differential equations, right, will get rid of constants. Take a time derivative of something that doesn't have a time derivative in it, boom, it's gone. Right? So you're utilizing that to your advantage to make the math easier. Okay. And in particular, what this gets us to is that beautiful little symbol that I was telling you about. You're going to end up, you're going to use this gauge, right? You use this definition everywhere here that you see B, you put that in. Everywhere that you see E, you put this in. Put all that into there. And the only thing you're left with is A's, B's, J's, and rows. Right? Okay, then you just collect everything. Put all the A's together, put all the A's together, and the V's together. And you get these two equations. You get That's pretty cool, right? Or no? Or no one cares?
I just have thoughts to do that in my free time.
Yeah. Well, remember that at that time, right? They had lots of free time. There was no TikTok, right? There's nothing like you just got married at like 14, and then all you did was sit and think for a long time, right? So here what you have is you have A's and B's. And you have one equation for A with a double derivative in space and a double derivative in time. That's only dependent on J. Okay. So moving charges create E fields. Yeah, that's 2 steps ahead, and the one in between is well, moving charges are the currents. Yeah, they create the vector potential. The vector potential derives from the current in the Lorentz gauge, right? And then the vector potential generates the B field. Good. Now the vector potential also generates the E field, as we saw. Right? So if I look at the second one, it says that V in the Lorentz gauge only comes from the distribution of charges. Okay. So you're still saying to yourself, well, what the who cares? And that's simply just because we like the D'Alembert. It's like, that's cool, right? You never used that before in your whole life. All right, so that is by definition, that is del squared minus not epsilon del squared. Okay. So we can write our 2 equations really simply. Okay, so that seemed like mathematical mumbo jumbo. We did learn something. Went from 4 equations to 2. Cool. All right. We have a relationship between them. So as long as we can define these things, we're good. So we just look at the distribution of charge. We look at the distribution of currents, and that tells us everything about our potentials. Okay, a lot easier said than done. Okay. So now the first question you may have is, okay. Had all this stuff about retarded potentials, and then I went on a tangent about that stuff there. So what we're going to be doing here is we need to combine these 2 pieces of information. So I'm telling you, if I just know where the charges are and how they're moving, that I can give you E and B. Good. And then I just told you that now I need to consider where the charges were, very specifically. Okay. So in practice, we just take this, the retarded time, and we put it here into J and into rho. Okay. Let's see how that's done.
We're saying we're making densities like in terms of time. So over.
Yeah. So remember that densities, right? So let me just write it out for 1 second. You'll see. Okay. So you might say something like this. V as a function of R and P. Is that okay? And we're just going to generalize these statements because right now I haven't given you a distribution, but once I give you a time varying distribution, we should be able to solve it. Right? So I might say something like this: 1 over 4 pi epsilon naught, the integral of rho R T over R theta. Reasonable? You've seen that before, right? Okay, so it's not surprising. So all I'm gonna do is I'm just gonna go like this. And I'm just gonna put the retarded time. You trust me? It's not a derivation. You shouldn't trust me. Right? It's totally hogwash, but it works. Okay? Yeah.
You get TR on that one too, or
Which one?
on the V?
Oh, yeah. Well, no. This is T. This is your current time. And this is the place that it's being recorded. You'll have to keep track of them. It's very annoying. The math is horrifying, but it's very consistent. Okay. And on this side too, we have A, R, T. How's this written? Not like that. Yeah. Yeah, probably. Good. Totally arbitrary, right? And yet it works. Okay. You might be really excited. You're like, wow, we can totally do this, right? This is awesome. And then you might want to do this, right? You might think to yourself, man, if I just, let's just do one more, just go one more, this. Reasonable, not reasonable. Looks like the same thing, right? Well, then why the f- did I teach you that?
Probably because the electric field that we were dealing with were so close to it, to like the observer, that you don't need to like account for restriction.
Yeah, retarded time definitely matters at farther distances, and we'll see that when we do the example. This one won't work, and in fact, this is not equal. Okay, because implicitly, what I haven't shown you, what I haven't seen here, is we have these del's inside of the v. So I just did another derivative, or so I, you call them an antiderivative, right? I did another integral, and it gave me the 1/r². This is not in practice how it happens. Because inside of t, how is t written again? T is did I write it? Yeah, that's right. Okay, so TR now has your time and your space together. So what happens if I do a time derivative of this? Not that big a deal. Okay, get rid of that. All right. See what the teacher does. What happens if you take a spatial trip?
Be able to get a second.
What's that?
Be able to keep the second.
No, in fact, you have to do chain roll.
Okay.
Okay, so in practice, you get something like this. Now, do I want to write it down? No, I don't. It's in your book. I'll do it just because. Yeah. All right, let me show you. So here's del v. Right, we're gonna write it like that. And I'm gonna put the del inside. Okay. Now I'm gonna have del rho. 1/r. Okay. And so you won't get that just one term that we saw before. When you do this all the way through, you may find yourself, especially if you're in spherical coordinates, asking what del of one over r is. You done this before? You did it in internet. No problem.
Kind of like the direct.
So the direct delta function being a point charge, the very center, right? So you'll end up with something like the individual charges times where the charges are. Seems like it doesn't make any sense, but if you think about it long and hard, it does make sense. Because all this is asking is where is the charge times is the charge there. Okay, so that's reasonable, right? Okay. Interestingly enough, the way that we wrote the retarded time was that it was t minus r over c. That's another arbitrary choice. Anyone seen the movie Tenet? Okay, so the hypothesis in Tenet is that you can do what?
Like reverse entropy or something like that.
Yeah, the entropy is just a choice, right? Like what I decided to wear today. So you could, that's a choice. Yeah, I know. We're not gonna talk about it. Okay, so you could have t go the other way. And those are called advanced potentials. In practice, the mathematics is the same. There is nothing that causally stops us from writing those things down. Are they useful? No. Right? Because they break the first law, which is causality. That we in fact have an arrow of time that we are all following. Okay. So in practice, we're going to use these ones. This one and this one. And this will allow us to do our problems. And they're going to suck. Okay. But they have really beautiful solutions. Mathematically, I mean, one of the things that's the hardest about teaching this particular section is the math is just horrifying. Okay. But the implications are so fascinating. So the main question we were asking earlier is how does light get from matter to us? And we will fundamentally derive that today. Okay, hopefully we can get through it very quickly. Did you write down what your answer was for that? You revised that answer over the weekend as you thought about it? What? Where does light come from? Oh, that's right. That's what we're doing. All right. Feeling at the bottom of my throat. It's the answer to light. That do be true though. I do know the answer already. You wrote it down though, right?
Yeah, we all know this.
You know? Okay, what's the answer?
You already know it.
I know it too. Oh, yeah. Good. So that's the point of the test, is for you to tell me what I already know, right? All right. Okay. Let's go to. You can kind of see, like, if you're in chapter 10 in the book, I know we stopped sort of halfway in there. They're just the worst. Just the worst equations. And these ones here, these are German. I don't know how to say that. Anyway, this person so recently found the E and B equations for the retarded time, right? Using that formalism. So for a long time, for like 50, 60 years, we just used this formalism. If you really care, you can derive the E's and B's directly from the charge distributions. So it's not worth it. It's a lot of math, in my opinion. They're just not necessary. Okay. But in practice, we're gonna see a lot of really interesting things here. So let me just let's start with the idea of where light comes from. I need a charge to move in order to generate B. Charges just existing already generates E. Okay. So let's imagine, if we will, I have a sphere. Okay. And that sphere has charge on the outside. If that sphere gets bigger and smaller, magic, don't ask how. Sphere just gets bigger and smaller, and all those charges move out and away, and out and away. Does that create light? Yes. Raise your hand for that creates light. Yeah, no instinct, right? Okay, good. We don't know what creates light. We haven't figured it out. We're just asking. So the parallel here would be, has anyone ever heard of frog? Hey, you know what a frog is?
Like a.
Yes, an amphibian, right? Green, brown, sometimes. Okay, how do frogs talk? They croak. And what do? They fill up a big bag of air and then they press it out. They fill up a big bag of air and then they press it out. Okay, so I'm thinking to myself, well, maybe I can generate light by taking these charges and filling it up some space and then collapsing it back down. Because now I have some time varying E, right? Maybe that creates light. Does that seem reasonable? It seems totally reasonable, right? Not possible. Okay, let me show you why. Hold on. That's my problem. Okay. All right.
Cool exercise.
Well, we're working backwards from history, right? So in fact, we're doing the opposite. You will not get so if you think about just a single source of light, you need there to be a dipole. And we're going to talk about why dipoles, quadrupoles are the only ways to get sources of light. Okay, I'm going to show you this. So first you have some dipole. Let's imagine, you can do this a number of different ways, it doesn't really matter. But let's imagine, okay. The dipole? Something like that. Okay. We're fine, very boring. If we had some magic way to send this charge up to there and this charge down to there, right? We could just like cycle the charge back and forth. Then you might say something along the lines of, well, Q at some time t is going to be Q naught cosine omega t. And that's the cycling frequency. Okay, you can send the charge up and down through the dipole and have them switch places. And you may remember that I made you sit through all these lectures on dipole moments, electric dipole moments. Ugh, what's any of that used for? Well, it's this actually. Okay, so let's see what this is. This is P naught, is a dipole moment, but now it's flipping, right? Because remember that the dipole moment is just Q times T. So in fact, we're going to do cosine omega T2. Or I should say as well. Okay. Is that reasonable? Okay. So let's write the retarded potential. I'm already going to have solved this. Yes, it's in. Yeah.
What was it, PFT again?
what was P of D?
Yeah, that's exactly.
It's their guide.
Okay.
Where P naught. Okay, so we can simplify this if we want. We can use the law of cosines. So you have some distance away from this. Draw this picture a little bit better. Let that need that. Let me redraw this picture. Reasonable? Same picture as before. Yeah. Yeah. And so we're just thinking about this at some distance far away. You have some dipole, magic dipole where you're putting the charge up and down. And the question is does this thing radiate? And we don't know. So we're gonna solve a bunch of equations, and the goal here is to get the E and B so that they go as 1 over R. Right? That's the goal. We can find terms that go like 1 over R. Great. When we do the multiplication of them, we end up with something that goes to infinity. So the law of cosines here allows me to write this as R plus minus is given by R squared minus plus R d cosine theta plus d over 2. Reasonable? So we're gonna make 3 major assumptions here. And this will be time for our first assumption. Okay. We are caring about what happens very far away. So the way that we would contextualize that is by saying that, go write it here. Assumption 1. E is smaller than R. Okay, reasonable. Okay, cool. Yeah, we're just gonna make some assumptions because otherwise the math is just, you know. Okay. D is 0, you get no potential. Because then the charges are just on top of each other, so no dipole at all. The D is inside of here. And this is present in both of them. Right? Okay, assaulting me. Okay. So if this assumption is true, then we can rewrite this as basically equal to R1 minus plus D over 2R. And so I can invert that if I want. And in the cosine part, we have some beautiful math that looks like this. Let's take a cosine of omega. And we're gonna do this for both of them because they're equivalent. R plus minus like that over C. Using the same assumption, we can write that this is. Oh boy. I'm just gonna give you the answer. I'm not gonna work into the steps, but it's like this. Right? Big oof. Okay, but it's just algebra. But no physics has happened yet. Okay, so we started off with this idea of retarded time. And what we needed to do was we needed to write it in a single coordinate system. So we said we're going to use the fact that there is a fixed separation here between D, and rather than considering the point at this charge at this point here, I'm going to reorient between D and R. So I can use a single long distance and one length. Okay. Okay. So now we can make another assumption. What kind of assumption do we want to make here based on how gross that looks? This is what I'm here.
Both the insides equal each other, you have the square inside, square, you have one.
That'd be very convenient. Yeah, yeah. We're gonna want this, right? Because this is like T minus R over C. That's in a common coordinate system. This is not the term that's giving me a nightmare.
Oh, nice.
Yeah, this one I don't like. Why? Right? That's just bad all the way through. And then what's this thing here? What's omega? Angular frequency, which is units of 1 over time, and D is, so this is like a velocity divided by a velocity of a very big velocity, right? So maybe we can use that to our advantage.
Oh, maybe we can
Make it go
only assume that.
Maybe we can make it go away, right? That's the whole point. I like to get rid of shit that's bad, right? So let's make the first assumption, right? Or sorry, let's make the second assumption, this assumption, which is that D is much, much smaller than
Or make it.
C over. Correct. That's a length, right? Right? All right. So if that's the case, then waves of a frequency lambda, we can relate them back to our omega here. So this requirement might also say something like we haven't even talked about waves, but I know we're headed there because I know where we're going. It's cheap. Okay. Okay, so this means that we can let's see, which of these terms does what?
So the first one, you'll just, first pass is the cosine of 0 is 1. And the second. one-
Wait, cosine of 0 is 1?
Yeah.
Hold on a second. Let's think about this really carefully. Cosine of x for small x.
Are you doing the small angle?
Oh, but can't we just say it's like really?
Yeah, like give it smaller than small, like 0.
Like nearly 0.
It's already in there, very assumption.
So we want this one to be 1. that what you're saying?
That's what I.
You want this one to be 1,
If it's
Yeah.
and this one to be,
0.
It's not 0, guys.
so this one here, we're gonna set equal to 1. That's the first order in the Taylor series. What's the first order in this one? Right. We're very gross.
There's one. Minus. Oh, that's one.
Oh, small angle approximation.
It's about 0.
No.
If X is 0.
Okay, so this thing we get rid of, and then this thing, I just get the inside order. Okay, got it. Okay. Okay, so let's put V back together. I'm gonna use all of this information in here. So V now is going to be equal to, oops. V to the R theta T, right? Because now I've introduced the theta in our coordinate system. So this is going to be P naught cosine theta, because that was on both terms, over 4 pi epsilon naught r. And then just have 2 pieces here, very reasonable pieces. Okay. That's a lot of mathematical mumbo jumbo. We need to make sure that whatever we're doing here is self-consistent with what we did before. So let's just check that I didn't fuck up. And I'm reading directly out of the book. If omega goes towards 0, what happens? Yeah, you just get the 1 over r, and then the 1 over r goes here, right? This first term disappears. And this thing becomes p cosine theta 1 over r squared. And that was our original V for a dipole. Oh, okay, so we did do it right, mostly. So now we have a formalism here that allows for both moving charges and stationary charges. This works for both of them, right? Okay. All right, so now we need one more assumption. This term right here, been thinking about these 2 different terms. This one is the term for the static field. And this is the one that if you look at it very closely, right, I got like a V over here. And the V is only dependent on 1 over r. By the time this comes in, it'll be 1 over r squared, and we've already lost the battle, right? So that stationary term, the term where it's not moving, is definitely not gonna send E out as one over R. Our bigger question is can we do something with all of this? Such that it does, right? So generally speaking, we can make this third assumption that we are in the radiation zone. Okay, not like the danger zone. Okay. All right. What does that mean?
Right.
Yeah, you can be like far away, right? So this, as I said earlier, is essentially the wavelength of whatever the oscillation is. So as long as you're like really far away from that, hundreds of times away from the wavelength of the oscillation, we can make the following assumption. Okay. So we just can treat it as this. Okay. Minus not. So here we have I, the vector potential, right? And you can do the same thing. You can set the current. Current would be dq dt. You can do this with A as well. Will not make you do that. But everything that we've just done is only for V, right? See how we have to replace the entire thing? Okay, so we do that again. Let's imagine that we go through it and we get the following. A looks like this. Not bad, right? You don't necessarily have an instinct for whether it's bad. But you may recall that in order to get E, we would have to do what to these two things? Yeah, we have to take derivatives, right? What kind of derivatives? Of what? But let's say we want E.
We want space derivative B and time derivative.
Okay, good. All right. Can we do that? I mean, it's so close to the end. Okay, so one of you is gonna do each of the jobs, okay? Oh, no, okay. So three of you will do the spatial derivatives of V. Three of you will do the spatial derivatives of A, the curl of A. And then three of you will do the time derivatives of A, sorry.
Everyone's what?
No, it's like this. I
No,
should.
Three, we've been tapped,
Three,
spatial.
three, and you can work together.
Yeah.
Shouldn't take you more than 10 minutes.
Should take for it to be. You say focus up.
Yeah, spatial derivative of B.
Yeah, so that are doesn't even affect.
Yes, I think
Thank you. We don't have to drive inside though. Inside is like a blind place where they can like eat.
Yeah.
So we got.
Well, this is the way to figure that. Spatial management, this would be.
Right. Yeah, my bad.
Yeah. That we want. Hard.
Yeah, we want. One picture.
Our little board.
I think
It is.
It is. I think she is. Okay, well, maybe, let's see what this is like.
Yes, we got negative. That's negative.
Yeah.
C, those are all constant.
Yeah, those can all go out in front. I thought we were, I thought we were like,
We look back at.
yeah, I thought it was Dell. Yeah,
Yeah, it's just a good one. And then worst case scenario, we do it again.
yeah, what, and are we using like? Oh, God. I mean, because like we have our.
We're not taking
Yeah.
taking a grade, and that's not a-
Oh, okay, so that's it.
Yeah, there's no.
But there's the product.
I just got it.
You do about that like the.
Figure it out later.
Why did we,
Just don't worry.
I gotta do it.
Okay, so
No, it's-
no, just look at the.
does it seem like cheating?
I could.
Don't look at. Let's control.
Hang on.
I'll do it, we'll check.
Because we have, yeah, we have like
If
one
you do-
over art.
Right here, we know.
And then we have-
species to-
So you did it?
Yeah. I don't.
Okay, it's easy to-
So will you test it?
Yeah.
Yeah.
Okay.
Did you just?
The only thing we don't necessarily use on this one is the rate.
Yeah.
So. it would be-
Oh, it is, ran to, looking at this page, because this is everything that's going to, because these are
No, it's like, no, actually, like if it's.
Okay, okay, well, good that we caught it.
Okay.
So I'm gonna be.
There it is. Be that and then both sides for a magnetic.
Okay, well,
So can we all agree that this is what we're trying to do right now? With the final line?
yeah,
Even city has to.
Looks good.
I'm not sure.
oh, this moves.
So everything in our, that's like.
So, yeah, here, you're gonna wanna make the changes of R's and thetas.
So.
Let's put it into R theta phi.
And this, they have PTVS.
Does that make sense why we would do that?
Yeah, cosine theta is a constant.
Okay, so notice that we had R and theta rather than C and phi.
This.
We can do the quote.
Then we gotta change.
Yeah.
That's, where did the coach?
I know.
I would just do like, R to negative one, and then you have sine of some function. You take the, yeah, just get that, yeah, just do the product rule,
Okay.
never do quotient.
So you just put that C here, but I'm gonna put something else.
You know, once.
And it's gonna help us. Because we have thetas, we have alphas, right?
Okay, so,
Yeah.
what he's talking
Right?
about.
Yeah.
Okay.
Instead of.
I'm gonna write it like this.
Is the derivative, I'm just gonna write the derivative.
Right.
Let me see.
No.
Let me see who it's at.
Would it be general?
It'd be, it's wrong.
No, it's the dude.
Good.
That is pretty good.
Is that okay?
We just like move in.
So instead of C pad, it's that,
And, like, make it just R.
right? And that way we'll all be in the same coordinates.
Everything.
Because before we had X, Y, Z, that was fine, and we could do just as a dipole. But really, we're thinking about it in the distribution, this theta can go in any direction.
Plus.
And since it's, axisymmetric, phi. Okay,
Like that's right though, right?
yeah. Yeah. Let's go. I told you it shouldn't take more than 10 minutes. I think the del cross A people are gonna be pissed at me. You're fine?
We're doing just.
Yeah, alright, pretty good.
Don't worry about it.
Okay, did you hear what I told them about making it turn?
I just don't remember. It's big.
I know.
Yeah.
So that's.
Yeah, there you go.
Yeah, I know.
Yeah.
See?
You know, just integrated.
Okay. Yeah, I don't have my friends.
Yeah, we're,
Yeah.
Let's make it-
wait, so we're driving, we're now driving in.
Yeah, don't forget about your chain rule, I think.
Yeah, we can-
it comes out.
Yeah, we need to change one inside of the.
Just the. Oh shit, well, the omega is large. Hang on, so omega just comes along for the ride. Well, what we're taking the derivative of is the
We're doing-
inside term.
So make over. Negative.
Omega.
If you do the check-in, yeah, I get one.
Omega is like-
So far, I only have like 5.
That's not more than thinker, you know?
Oh, okay. Two negatives.
Yeah.
All.
Everything you've done. Yeah. We'll talk about that in 7 minutes.
I would just take out this is the comments,
Yeah,
that's the.
well,
seal.
this one's no one understands.
We could factor out the negative, and think it goes away.
I might have done something on this one.
That's like, our.
Say it again.
One.
Yeah, negative one art story, yeah, negative. Yeah.
I hope this didn't throw people off.
Oh, yeah, I didn't even look at that. Do we have that for B?
Do we have to do?
We don't have a component. for
What,
because
which
it's scale.
coordinate system do
Okay,
you use?
cool. Never really had a call.
Okay, I would use spherical here.
What coordinate is that in spherical? Is that what it is?
It's like this.
Oh,
It's okay though. If you didn't do it, that's fine. But that you should end up, the del cross people should end up with one component.
yeah,
Is in phi. You have it in phi or Z?
it's in 5, but I did cylindrical. Because I thought that was,
Okay. Yeah, I mean, it doesn't have anything to do with phi and it doesn't have anything to do with Z, so those derivatives should both cancel, right? It's probably very close. My notes will be in spherical and yours will be in
So we
symmetrical.
try to- this is what we got.
wait, what did you say
Yeah,
that,
purely
that
derivative.
Derivative,
that's.
yeah, just for the derivative,
This piece here.
yeah,
And then we just gotta multiply it all the time.
yeah. Just repeating it.
How we doing? This is what I got.
That's okay.
And John agrees with it. This is.
I'm not doing that, that's what you're saying.
I'm factoring in like the constant front.
Yeah,
Oh, this is just,
What'd you
help
get
me
that?
with the product rule. Because the, or the
A
change.
bunch
to
of
the
stuff in
ZP
the
prime
front and
plus
then
B
like a
prime.
cosine
That
minus
is-
a sine.
This is how I learned it in high school.
A bunch of stuff in the front and a cosine minus a sine.
And then like,
Like all that same.
honestly,
stuff
I'm
with,
fine with just leaving it like that.
I am too.
Yeah, like,
Okay.
no need to distribute, it's all.
So like you have something like this,
Nothing canceled.
So therefore, and we just did the gradient.
right?
Yes,
It's a gradient.
that'll be. With respect to art. I think it's like, I would just. They know they're on, right?
Yeah.
Like, oh.
But we have to do it because
No.
there's R in.
Nice.
right? And that gives you. What'd you guys get?
Yeah.
Yeah, the gradient.
No.
Okay. Yeah.
It was like, oh, fuck.
Okay, so for that spatial derivative, we got
I,
negative P naught omega. I'm just listing the.
How many terms do you have?
Just
One, two.
Okay,
no,
did
no.
you use any approximations?
No, should we had it?
Maybe.
Shit.
Think about the function of your potentials right now. Del cross or del V.
Mhm.
What are you trying to get?
We just want one over R, right?
You're trying to get E, right?
Yeah.
And you want E to look like
One over R.
1 over R. So any terms that are more than 1 over R, you're probably gonna wanna drop those, right?
I swear, like we have.
What do you tell me? I don't know.
we have R squared.
If you have a 1 over R squared, that's gonna be bad for our potential. That term's gonna disappear, so we don't even care to compute it,
Okay.
right? That's our static term that I threw away over here,
Yeah,
right? We didn't even bring it with us.
got it.
Left it at home. Bad dog. So reasonable?
Yeah,
Okay.
well, separate from then that assumption. We
Yeah.
have one term.
Good, and what's that one term look like?
So it's the bunch of constants that are still out in front. And
It's actually not too bad.
factor out, oh, okay, yeah, you can factor out what you got, it's fine. And then, I guess cosine of the inside omega quantity t minus r over c,
What's that?
and then over,
Over R.
yeah,
We fully calculated and we didn't make the assumptions.
yeah, that
But
assumption,
that is our,
right, yeah, we just let like the cosine thing, that's. Got it.
Okay, so now you have all your pieces. Now you have E, now you have B, they just don't look like you're used to them looking. Right? And in fact, when you look at your E was, which parts here?
Top and the bottom.
This one and that one, right? So now we'll notice here, okay, so this has a piece with R. Okay, that looks pretty similar and that does look like a negative. So they're gonna cancel. So all the work that you just did for us was to show that this and this disappear and we only have a theta piece. In an E. Okay, so E. So E. Phrases did not work at all. So E goes like theta. And what about B? Which one of these tells us B?
The middle one.
The middle one.
oh, okay, so that, it's not
Oh,
R.
so
Ah, there's like 5.
So
Okay.
propagating in R.
Ah, okay. So S goes like
Equals B and R.
R. Okay, so these waves are propagating in R. And let's just double check that they make it to infinity. How many R's do I get? I get 1 here. This one is not going to contribute. This one is a loser, right? R times R, not going to add. But R times this piece, that's okay with me, right? And similarly, if I look at this piece with this piece, okay, these two pieces cancel. But this thing here, sine, just has a 1 over R. So I get a 1 over R here from the E. And I get a 1 over R here from the B. And this goes like 1 over R squared. So the power with R equal to infinity, oh god. It's fucking random. Is not 0. So there
Oh,
we get radiation.
so light propagates from waves that are like spherical waves?
So interestingly enough, you have to look at how the distribution of these waves are. Now I said that they go in this way, but they do have a dependence on theta. And in fact, that means that they're not spherical waves, they are donut looking waves. So they will not propagate in the Z direction at all. It will only propagate out like this. And we're gonna see a different example of this when we talk about antenna. This is how antenna work, both receiving and giving. So all you have to do is force a current through a wire, okay? And then remove the current from the wire, and then force it to the wire, and then remove it, and that time-changing current through the wire produces radio waves. The what?
Frog in the water.
Yeah, frog in the water doesn't, and we'll see why that is, maybe as a homework problem.
I mean, like how it's like a donut shape, kind of like that.
Oh, the ripples, yeah.
It's like.
Oh, yeah, no, so, yeah, the previous example where you don't have an electric monopole, electric monopoles will not generate radiation. And maybe I'll find that one as a homework problem. Because you love homework, right? Okay, so the things that you actually stay here for, there's no exam on Thursday, that exam will be on Tuesday for people who want it. If you have not signed up for a check-in, send me a Slack message. I will not be here on Friday, so it'll be really hard to check in with me. I'll be on a plane to Tokyo. And bring all of your homeworks, everything you've done, including stuff that I haven't graded. Bring in stuff that you've turned back in a second time. Think about the week that we have quote unquote off as a time to like recharge, rest, look at your work, try to get better. Okay?
So you're gone Friday, Tuesday, Thursday?
Yeah. Well, I'm gone
Well,
the whole week and Friday.
Probably last.
I think the weather would be bad.